conductors are a broad class of materials in which inside there are charge carriers that are free to move. Now we'd like to just represent a conductor as a conducting object, and I'll make it a two-dimensional picture of it. So this is the conductor. Here it's hollow. And we would like to consider what happens in the case of electrostatic equilibrium. Now we have to be careful here because we're not talking about non-electrostatic forces. We're just considering electrostatic forces. So let's take a look at the conductor and let's blow up the interior. So here's our conductor. And the main property of conductors is that the charge carriers are free to move. They'll move around under the influence of mutual electric forces until finally they don't move anymore, and they're not moving anymore when the electric field, that's right, inside the conductor is zero. And this is the crucial condition for conductors at equilibrium. Now, as I said before, we may consider non-electrostatic forces coming from chemical reactions or other types of instances in which you could have a non-zero zero field in a conductor and still have electrostatic equilibrium, but we're not considering that case right now. We're just considering pure conductors and the charge carriers on them. And what we'd like to do is look at the consequences of this condition that at equilibrium, the electric field inside the conductor, the metal of the conductor, if you like, is zero. Well, the first thing we can say is that every point in the conductor is at the same potential. Now, that may seem a little unusual at first, but let's look at the condition. Suppose we have the conductor, and we consider a point A and another point B, and we take any path going from A to B. Well, the potential difference between these 2 points is equal to the integral minus of the electric field along that path from A to B. And because the electric field inside the conductor, I'll just put E in is zero, this integral is zero, and that implies that the potential at every 2 points is equal. So now we have two crucial properties about the interior of the conductor. We can call this 1, and we can call this 2. Now, what about the charge carriers? Well, the first question we want to ask is it possible that there are charge carriers in the interior of the conductor, in the metal, at electrostatic equilibrium? So let's take a little piece of this metal. Let's imagine here, suppose we do have a charge Q. And let's blow this picture up. So here's our charge Q. Our conductor is big. And now imagine that you put a little Gaussian surface around this charge. Q Gaussian, radius epsilon. Then we know that electric fields should emanate from this charge. And if this epsilon is very small, they'll go out of this Gaussian surface. And so we can say from Gauss's law that the integral of E dot dA through our Gaussian surface should be equal to 1 over epsilon naught, the charge enclosed. And here in the limit, as epsilon goes to 0, let's see what would happen. Well, the electric field, this is the inside of the metal of the conductor, so this side is 0. And so if we're surrounding our point charge with one tiny little Gaussian surface, the conclusion is that Q enclosed is 0. So there can't be any charges in the metal of the conductor by Gauss's law. Now, from a physical perspective, that makes sense too, because if there were charges in the conductor, then they would exert forces on all of the other charges in this conductor that are free to move, and the charges will keep on moving. So again, our third key condition at electrostatic equilibrium is that the charge density, so this is rho, is 0 inside a conductor, i.e., there are no charge carriers in the interior metal of the conductor. Keep in mind, we're not talking about this hollow region, we're just talking about the conductor. And those are our three crucial conditions for the conductor. Zero electric field, any 2 points on the conductor are at the same potential, and there are no free charge carriers in the interior of the conductor. Now, where are those charge carriers? They're on the boundaries, and we'll study that next.